Welcome, and thank you for joining this executive summary webinar, The Architecture of Autonomy, Distributed Artificial Intelligence as a Native Capability of Future Wireless Networks, prepared by the Alpert Research Team. We are going to explore why distributed artificial intelligence, or DAI, is rapidly moving from just a theoretical concept to an intrinsic native capability within 5G advanced and 6G wireless systems.
And it is essential to understand the baseline context of this evolution. Because for decades, wireless networks were designed with a single overarching philosophy: be highly efficient, but ultimately be passive conduits for transmitting bits from point A to point B. The network was just a pipe, but that era is fundamentally over. To handle the staggering complexity of hyper-connected next-generation environments, the network itself must become an intelligent, self-evolving infrastructure.
Which makes sense, given the sheer volume of devices today.
And we have tried overlaying centralized, cloud-based AI on top of these networks to manage this complexity, but that approach is structurally failing at scale. We are hitting a wall, which requires a fundamental architectural shift.
We have these massive, incredibly smart data centers.
The hyperscalers.
Why is the centralized model actually breaking down?
The core problem is scale. Scale compounded by an unforgiving demand for ultra-low latency. We are moving into an era characterized by industrial automation, autonomous mobility, mission-critical applications.
For milliseconds matter.
Milliseconds absolutely matter. A sensor on a factory floor detecting a millimeter of deviation to be transmitted all the way to a centralized cloud, processed, and then a command is sent back. Yes, that round trip simply takes too long. When you multiply that by billions of connected devices, the physical limitations of our networks just begin to buckle. It introduces unacceptable latency, it consumes massive amounts of backhaul bandwidth, and it creates severe bottlenecks.
If we are talking about mission-critical applications, let's consider remote robotic surgery.
That's a great example.
Imagine a highly specialized surgeon in New York guiding a robotic arm to perform a delicate procedure on a patient in a rural hospital. If the AI assisting that operation relies on a centralized cloud,
in a traditional centralized setup, you could easily be looking at a 200 millisecond latency for complex computer vision tasks, which sounds fast to a human, but in the context of robotic surgery, 200 milliseconds means the AI might reconstruct a tumor where there isn't one.
Lives are literally at risk when intelligence is that far away from the point of action. The current centralized AI model is essentially a monolithic brain in a jar. You have this massive, incredibly smart entity sitting far away in a data center, but it requires all the raw, heavy data to be constantly forced inward just to function.
The technical limitations of that brain in a jar are profound. Beyond the latency we just discussed, there's the massive backhaul bandwidth consumption.
Because you're sending everything.
Every single piece of raw data. We simply cannot afford to lay fiber to every single small cell and sensor to send every piece of raw data across the network core.
It's financially and physically impossible.
And furthermore, aggregating sensitive real-world data into single repositories creates massive security vulnerabilities.
So if the brain in the jar is failing, what is the alternative?
The Alpert Research Team defines distributed artificial intelligence as an architecture where the complete pipeline of intelligence, so that's sensing, learning, reasoning, and decision-making, is spread across multiple autonomous nodes. These nodes can be end-user devices, edge servers, or core network elements. Instead of centralizing raw data in one distant cloud repository, the intelligence is pushed outward. You process the data directly where it lives. It shifts the network from a single brain to a collaborative team of autonomous agents embedded natively across the entire network topology.
That structural alignment sounds incredibly resilient.
The operational impact on the network itself is massive. By keeping data local and relying on mesh connectivity, where edge nodes coordinate peer-to-peer, the network drastically reduces its dependency on backhaul links,
which solves the bandwidth issue.
And it creates a highly fault-tolerant system. Additionally, it ensures data sovereignty, as the raw, sensitive data never actually leaves the local domain.
Let's unpack how this actually works architecturally. But how do these distributed nodes actually learn anything if they aren't sending all that raw data back to the center?
The foundational mechanism driving this is called federated learning, or FL. In a centralized system, you move the data to the model. In federated learning, you move the model to the data. It works like this. Each autonomous device downloads a baseline AI model. It then trains that model locally using its own private data, utilizing its own onboard processing power. Once it has learned from that data, it does not send the raw information back. Instead, it computes a local weight update, essentially a mathematical summary of what it learned, and sends only that update back to a central aggregator. The aggregator combines updates from thousands of devices to create a smarter global model, which is then sent back out.
If the central server cannot see my actual data, how do those abstract mathematical updates actually improve the global model?
A helpful mental model for this is the hiker in the fog analogy, which illustrates a concept known as gradient descent. Imagine you are a hiker trying to find the absolute lowest point of a massive valley. It represents a perfect AI model with zero errors. But there is a thick fog. You cannot see the valley. The only thing you can do is feel the slope of the ground. That slope is the gradient. You can tell which direction is downhill, so you take a small step in that direction. In federated learning, each device feels the slope of its own local data, and it sends back the direction of that step. The central aggregator takes all those different steps from all the different hikers across the mountain and averages them to figure out the best overall path down. They share the direction of improvement, not the landscape itself.
That completely flips how I thought machine learning had to work. Swarm intelligence or multi-agent systems. How does that differ from what you just described?
Well, federated learning is highly effective, but notice that it still relies on a central aggregator to compile the updates. Swarm intelligence removes that central coordinator entirely. It enables fully decentralized, self-organized systems. This is inspired heavily by biological phenomena designed to achieve complex, adaptive global behavior purely through local peer-to-peer interactions.
Like a flock of birds.
Exactly.
When you watch a massive flock of starlings moving in the sky, creating those incredible sweeping shapes, it's not like there's a CEO bird at the front shouting orders to everyone else.
Biological swarms are the perfect analog.
Yeah.
If there were a leader bird and a predator removed that leader, the entire flock would crash in confusion.
Right.
Instead, the flock is incredibly resilient because every single bird is just following a few very simple, decentralized rules based only on what it can see immediately around it. In a digital swarm, those rules are roughly 1. Do not crash into your immediate neighbor. 2. Match your neighbor's speed and direction. And 3. Move toward the center of your visible neighbors.
Applied to wireless networks, these local rules allow nodes to govern themselves.
They allow nodes to dynamically allocate spectrum, route traffic, and manage interference at a microsecond scale without ever asking a cloud controller for permission. There is no central point of failure. The global objective, a perfectly optimized wireless network, emerges organically from local action. A localized network anomaly can be contained and resolved by the swarm instantly.
We are talking about fundamentally re-architecting global telecoms, so there have to be a bottleneck somewhere in this process.
The research highlights a major hurdle known as the irony of distributed learning. We have established that distributing the intelligence solves the core compute and privacy problems. However, the constant exchange of massive model updates those mathematical steps down the mountain creates an entirely new bottleneck.
Because modern neural networks aren't just a few data points, right? We are talking about models with millions, sometimes billions of parameters.
And transmitting those massive parameter updates across wireless channels with limited bandwidth causes severe network congestion. In large-scale DAI deployments, the actual computation on the device might be lightning fast, but the communication, the time spent transmitting the updates back and forth over the air, can consume up to 80% of the total training time. Communication, not computation, becomes your dominant constraint. Bandwidth essentially becomes the new compute.
So how do we solve that?
Researchers are actively integrating two highly effective mitigation strategies, sparsification and quantization. Sparsification is fundamentally about filtering. An algorithm monitors the thousands of parameter updates generated by a device. It enforces a strict threshold. If a parameter only changed by a microscopic amount, meaning that specific part of the model didn't learn anything highly significant during that round side, the system simply rounds it down to 0 and doesn't bother sending it at all. It only transmits the most important, loudest changes, making the data package sparse. Quantization addresses the precision of the numbers you do send.
If I need to communicate the concept of pi to you, I could send a highly precise 32-bit floating point number, 3.14159265, and so on. That takes a lot of bandwidth to transmit. Or I can crush it down and just send 3.14. You still understand the mathematical concept, but the data payload is tiny.
You reduce the precision to save bandwidth, but in the context of distributed AI, they push this to the absolute extreme, sometimes crushing the update down to a 1-bit value. But here is the remarkable finding from the field tests. Despite sending these heavily compressed, imperfect updates across messy, real-world wireless environments, neural networks are remarkably robust.
They can still learn from just a plus or minus.
Because they are learning aggregate patterns over thousands of iterations across thousands of devices. The direction of the learning is far more critical than the microscopic precision of a single update.
So the sheer volume makes up for the lack of precision.
The global model still converges accurately, proving that DAI can operate efficiently, even on severely bandwidth-constrained edge devices.
That handles the bandwidth constraint, but what about the quality of the data itself? If my phone is training a model based on my life, that data is going to be incredibly specific to me.
This brings us to a concept the research calls non-IID data. It stands for non-independent and identically distributed. It means the real world is entirely heterogeneous. In a centralized tech lab, your training data is perfectly shuffled, balanced, and clean. Out in the real world, the data on every device is radically different.
Right, so if my phone is learning my typing habits to improve a predictive text AI, and I am a medical doctor, the local model on my phone is going to optimize heavily for complex medical terminology. But if you are a teenager who games all day, your local model will optimize for video game slang. Our data is completely different. If the central server just blindly averages our updates together, wouldn't the resulting global model be terrible for both of us?
It would be, and that is a significant hurdle that the industry is actively solving. Simple federated averaging is evolving into more localized, hierarchical models. The network might group similar edge devices together, so all the doctors' phones learn from each other and all the gamers' phones learn from each other. Alternatively, architectures are moving toward personalized federated learning. The global model provides a baseline understanding of language, but the local device retains a specialized layer just for its user that never gets averaged out.
All right, let's look at the timeline here. When is this move from experimental lab work to actual deployment?
The integration of distributed AI into telecommunications is an architectural revolution. AI is actively entering the global standardization roadmap right now. Specifically, within the 3GPP Release 18 and 19 frameworks, artificial intelligence and machine learning are becoming native to the air interface itself. The network fundamentally transitions from the paradigm of reactive troubleshooting to proactive autonomous management. In a legacy system, a cell tower blindly handles traffic until it reaches maximum capacity, at which point calls drop, speeds plummet, and alarms go off at a central network operations center. A human operator or a rigid algorithm then tries to fix the bottleneck after the damage is already done.
But with a DAI architecture, that cell tower has its own autonomous agent.
It possesses local reasoning capabilities. That agent utilizes historical data, local weather inputs, and neighborhood event schedules to predict that a massive rush hour traffic spike will hit exactly at 5:00 p.m. And because it doesn't need to ask a centralized cloud for permission, it acts on that prediction. At 4:55 p.m., the agent autonomously powers up extra antenna arrays, adjusts the beamforming to target the specific highway on-ramps, and coordinates with neighboring towers to hand off non-essential traffic.
It completely prevents the congestion before a single user experiences a drop in service. The implications of this shift must be highly quantifiable. We aren't just talking about cooler technology. We are talking about operational outcomes and return on investment.
Implementing these distributed AI architectures yields a 21 to 35% reduction in operating costs. It is largely driven by massive improvements in energy efficiency because towers can autonomously power down when not needed, and a sharp decrease in the need for human intervention in network management.
Plus the performance gains.
Furthermore, dynamic spectrum allocation and localized processing deliver 2 to 15 times throughput improvements compared to legacy approaches. It marks a definitive shift from managing static infrastructure to orchestrating an intelligent, self-optimizing ecosystem.
What is the bottom line here? How urgent is this architectural shift?
Synthesizing the research, the strategic reality comes down to technology readiness levels, or TRLs. The core foundational technologies we have discussed, federated learning and edge AI, are not science fiction.
They're here now.
They're currently assessed at TRL 7 and 8. That means they have been validated in operational environments and are nearing widespread commercial deployment. Swarm intelligence and fully decentralized multi-agent systems are slightly further out, currently sitting at TRL 4 to 6, with major 6G pilots slated for the 2028 to 2030 timeframe.
So the window for strategic positioning is right now.
Early adopters who understand this architectural shift, who begin integrating edge compute capabilities and privacy-preserving learning frameworks today, will gain massive efficiency and performance leads as these standards solidify. If you are building network strategy based on hauling all data to a central cloud, your architecture will soon be fundamentally obsolete.
Thank you so much for joining us for this deep dive into the Alpert Research Team's executive summary. We've covered the scale challenge breaking centralized networks, the mechanics of federated and swarm intelligence, how to solve the communication bottlenecks with sparsification and quantization, and the standardized reality of AI native 6G.
It's a lot of ground to cover, but crucial. Distributed artificial intelligence is central to the evolution of 5G Advanced and 6G, redefining how wireless networks are designed, operated, and trusted in the autonomous era.
It really is the future of the field.
And if you are interested in gaining a deeper understanding of the transformative power of wireless technology, the Alpert Research Team runs webinars where they explore these cutting-edge wireless innovations, their applications, and their implications. We encourage you to click the links below to learn more.
It's well worth your time if this topic is interesting to you.
Thanks for listening. We'll see you next time.